Yeah. Okay. Dear colleagues, let us start our seminar. Now we have a continuation of the talk by Volodya Rubtsov, and we think that it will be not the last part, and we will have a third part of this talk on the next week. So we can continue. Volodya.
Okay. Hello. Thank you very much for this opportunity. And I'm sorry for my so long talk, but logically I should ask you a favor to give me a certain part to tell you. Then it will be much better from my point of view, at least if you want to understand and to enter in the subject more seriously. Otherwise, it will be very superficial. Okay, I will just briefly remind you that we discuss so-called multiplication kernels, and this is a general background of all these stories. But formally, we will speak mainly about the kernels related to special operator, which we called quantum projective space operator, or Bessel operator for simplicity. And with the another part of the story, it's a story of two families of polynomials, symmetric polynomials of three variables, which are dependent on three parameters. And these polynomials we refer as Buchstaber and generalized Kontsevich. They appeared in absolutely different parts of mathematics, but they are related by the construction with the help of two-valued groups ideology and generalized shift operators ideology, which is also related to this multiplication kernel background. This type of polynomials I described, and then we came to our story, and I told you about motivations, about reasons why we are interested in this, gave some literature remarks, and then start to explain the first serious background and first serious motivation, which goes back to mirror symmetry of Gieventhal, Yao, Liang, and Liu theorem. And we stopped in this point last time. So we spoke about enumerative invariance of Gromov-Witten type, which encoded in so-called instanton numbers, which you can get from the approach of Candelas and company, and proved mathematically by Yao, Liang Liu, and Gieventhal. And then I stopped at the description what's happened in general with so-called Calabi-Yau differential operators, and do we have Calabi-Yau in our story? So Calabi-Yau differential operators for the case of operator of order 4 studied by Gerd Almquist, who unfortunately died a few years ago, and Dukov and Straten mainly. They have a huge list of such operators. These operators are the Monique operators of order 4 with respect to this logarithmic derivative, as I told you, and they have the following main features. Singularities are regular. The origin is always maximal unipotent monodromy point. Then they are self-dual in the usual sense of differential operator conjugation. And what is very important for us, they have the following integrality conditions. So if we have an analytic solution phi sub 0, it has integer coefficients in series. The corresponding mirror coordinate, which is, as I explained from the construction of Candelas and company, and Yao and collaborators, the exponential of relations phi sub 1, phi sub 0 is also integer. And it gives the series of integer coefficients when you go for Lambert decomposition of Yukawa coupling. So if we have all this stuff, we will speak about Calabi-Yau differential operators for n equal to 4. Now, my question, why it is interesting? Because the Calabi-Yau differential operators very often are related to so-called toric hypersurface, Calabi-Yau toric hypersurface, as a period functions. So analytic solution of these differential operators can be expressed in terms of residue theorem. These integrals are over n-1 product of S1 times S1 times S1. And this is the logarithmic measure, and the divisor of denominator, divisor of zeros, gives by Laurent polynomial from variables x1, xn, and inverse, because it's Laurent polynomial, and integrality of the coefficients of my function, of my solution for Calabi-Yau, explains by the following formula. The coefficients of generating series for this B sub k, they can be computed like a residue in zero of k's degree of this Laurent polynomial, which usually people call superpotential. Batarev discovered that, sorry, what's happened? I don't understand. I'm sorry. Batarev discovered that if we take, so do you see my slides?
Yes.
Okay. Batarev discovered that if you have this zero locus, w of x equal to 1, then it can be convectified to Calabi-Yau hypersurface if the corresponding Newton polytope for this is reflexive. I will go to this question a little bit later. And now I want to come back to something very, very simple. I just want to explain what kind of operators we will have in the case of so-called quantum or Bessel case. So if n equal to 1, then this n Bessel operator, one Bessel operator, it is just a absolutely trivial operator, x d over dx, and the problem with the eigenvalue lambda gives you immediately exponential solution, exponential to lambda x. And of course, if we take product of the two exponentials, it is the exponential of x plus y in the exponent, and we can represent it in our favorite multiplicative kernel form, taking the delta function as a kernel. And this other form of this representation, it is of course Cauchy residue theorem with a rational kernel when z, it's our integration variables. This is my exponent in the point z, and this my rational kernel 1 over z minus x plus y. So in the case of n equal to 1, the Cauchy formula gives absolutely nice and elementary rational answer for multiplication kernel. Of course, nothing interesting, but very, I would say, explicative. It means that using Cauchy formula, you can produce many interesting other kernels, probably, for other operators. Now let's consider n equal to 2. N equal to 2 is much more interesting because for n equal to 2, you have second order equation. And this equation, now it is very, very close to a real Bessel equation and real Bessel function. Namely, we can normalize the solution of this eigenproblem. We denote it by J sub 0. And it is explicitly this degeneration hypergeometry from which I have started, with special value of lambda and special value of parameter in the Pochheimer in the denominator. So this normalized solution can be expressed in terms of modified Bessel of index 0 taken in the point 2 times square root of lambda x. It's just a change of variables if you want. But the representation is quite nice without minus times minus 1 in degree and some fractions. So it is a very nice hypergeometric representation. Then multiplication formula, which goes back to Sonine and Gegenbauer for this J sub 0, has very, very nice algebraic expression in the denominator. So my kernel is 1 over this square root of sum of squares xy plus y square plus z square minus etc. And of course, it is interesting and very easy to find the differential equation for this kernel. It means to find to which operator this kernel gives a solution. This operator has order 1, so the equation is the following. This expression under the square root gives you explicitly the singularity locus in front of the first derivative. And if we take the initial value x, say, equal to 0, you see this beautiful Sonine Gegenbauer again. I don't understand what's happening. Sonine Gegenbauer kernel, if you take x equal to 0, it's 1 over z minus y. And because of symmetricity, if you change x by y by z, you always have this initial data of rational type. So we will call it Clausen-Sonine. Clausen, because if you will see that Clausen relates to this formula when you go to diagonal, we will see it very soon. So let's go to this equation on the diagonal. So we take this G0, take now the solution of this modified Bessel for n equal to 2, and then we are discovered it is just integration by part, easy to check, that square of this solution satisfies to this cubic equation. And this cubic equation is nothing but symmetric square of Bessel operator. So Clausen duplication formula in integral form, it means that if we take the product of this degeneration hypergeometry, in square, taking x equal to y, satisfy to the following form. And our kernel transforms in very, very simple function with this square root. And this very simple function has binomial coefficient development. And people who are very well in combinatorics, they immediately recognize in this function which is a cousin of so-called this is not exactly the generating function, but this function satisfied to some differential equation with generating function of very popular combinatorial objects, which it's related to Narayana numbers, and also it relates to Catalan numbers. First Catalan and then Narayana. For Narayana, I will show you more precisely later. So the demonstration is straightforward. It's just different. You should just derivate this by parameter and check that it satisfies. And also integration by part also gives you this answer. It's very, very beautiful formula, which we will call Clausen. Now, what's happened for any n? Of course, it is much more interesting considering general situation, general kernels, and general combinatorial developments. Here, I'm half on the land of so-called experimental mathematics. It means that some things we are able to prove, some things we are just able to compute and to show, and we have no strong mathematical demonstration, but we have some conjectures based on our computer experiments. So we consider n arbitrary. So this is my n Bessel or quantum equation, and this equation admit the following solution, which is a straightforward generalization of my solution for n equal to 2. Now I take in hypergeometric series here n as a degree, and for simplicity I will take lambda equal to 1. Then this solution has the following representation. First of all, if I apply Laplace transform to this function, I obtain very nice binomial series with the coefficients n times k factorial over k factorial n zk. This is a very famous and very simple type of series. And then I want to compute the formula for a kernel. It means that I want to present the product of my solutions in different points in integral form. First, I want to present it again in the form of series in two variables with binomial and factorial coefficients. It is straightforward from this representation. And then I can try to find analog of period, so-called quantum period, because it's a quantum operator, analog of period for my function. It means I would try to find a representation of my function in terms of Cauchy type residue, or more precisely Poincaré type residue integral. So this formula we have. And we are able to prove some theorems, which I will formulate a little bit later. So we take measure of logarithmic type. Our integral always over torus, which is a product of n minus 1 times spheres S1. And the function which we integrate, it's an exponential of this Laurent polynomial, and this Laurent polynomial very similar to so-called Dwork family of Laurent polynomials, or Dwork family of superpotentials in exponential form. More precise statement I will give you immediately. Now, let's go to my representation of this product. I'm seeking this integral representation with some function k of x, y, z. This function is homogeneous, so I can replace it by function h of ratio x over z, y over z. And then my representation in terms of double series, I will go to new coordinates, big X and big Y, which are ratios of my small x over z, y over z. So I'm trying to find this function. And for n equal to 2, we know this function. This function is 1 over square root of this conic. You remember this conic, which I denote d sub 2, because I will have a formula for any n in few minutes. And this conic d2, which is under the square root of Clausen and Sonine kernel, has a very nice geometric interpretation. If we go to square coordinates, replace x, y, z by u square, v square, and w square, then this conic will go to quartic, which initial form of Sonine Gegenbauer kernel. And this quartic can be factorized in very nice formula, which, of course, you can recognize as a Heron formula for square root of triangle times coefficient 16. So square of triangle with lengths of different codes u, v, w gives you the following configuration, which we call Heron configuration. This is our circle inscribed in the triangle. Each triangle has this tangent point in the middle, and this is our zero locus for you remember this zero locus is the coefficient, the zero locus of the coefficient of my kernel equation, this one. Now, what's happened for any n? For any n, we are able to prove the following theorem. Let's consider the superpotential W sub n, which depends on x, y, z as parameters, and big y1, y2, yn minus 1. So it's a function of big Y with 3 parameters. And this function has the following form. X times product of 1 plus y from 1 to n minus 1 plus y products of 1 plus y j 2 minus 1 in inverse and minus z. So this is a hypersurface. The kernel represents like integral of Cauchy type, or if you want Poincaré residue, with this Laurent polynomial in the denominator, and this is the product of usual product of toric measure. The singular locus of the corresponding d-module Hn also has very nice geometric interpretation. It consists of my standard triangle xyz equal to 0. Why it's like this, remember? But now we have a rational curve of degree n with n minus 1, n minus 2 over 2 double points. And this curve intersects the coordinate triangle, this triangle of x, y is equal to 0, in these 3 midpoints, like it was in the case of Heron configuration. So we have polynomial symmetric equation delta n of x, y, z. If we replace x, y, z by nth degree, like we did it for n equal to 2, v and w to n, then this equation factorized in the product of linear terms, and coefficients in v and w are square roots of degree n of unity. So we have the product over lattice over degrees of unities in W and eta, and we have this generalization of Heron configurations. When we write it in terms of initial x, y, z, then we obtained beautiful symmetric polynomial. For n equal to 3, we obtained this one. For n equal to 4, we obtained this one. And then I remind you, for n equal to 2, it is this one, and 3 and 4, and etc. We have such representation for any n, and observation is that each polynomial of this zero locus, it is polynomial which relates to some n valued group law. It means for n equal to 2, when we have this square, this Heron configuration, this polynomial, it's a polynomial of two-valued group, which I started with. And I showed you this two-valued group in the very, very beginning of my talk. I showed you this. It's a law which relates to addition law on C. Here it is. Here it is. This is exactly the n equal to 2 value, my to example. And it means that any quantum Bessel polynomial somehow relates to n-valued group multiple law, n-valued group. So it was the first interesting observation from our theorem. Second interesting observation is the following. Let's consider how this Clausen duplication can be generalized for any n. It means that we take, again, restriction for diagonal for our solution g to n. So g to n times g to n gives you this series. The coefficients c sub n of this series, they are very, very nice sum of binomial coefficients. And also we can use the interpretation of this product in terms of so-called Adamar multiplicative convolution. Adamar product or Adamar multiplicative convolution, I remind you, it's a product of two series, f and g, with coefficients a and b. And it gives you the third series, this convolution, whose coefficients are just product of coefficients of this series. Very simple. And straightforward observation that this convolution, it is very well known, can be written in integral form as the following residual integral. So it's integral of f x over t times gt with this logarithmic measure dt over t, integral over t equal mod t equal to 1, for example. And then you can check that the square of this solution, my equation, can be represented in convolution form with the series with my Cn coefficients. It means that there is a kernel function k of x, and this kernel function can be represented in this integral form. And this kernel function is nothing but my h function taken in diagonal. Let's compute it more precisely. So this for any n, this is series for this generating series for my kernel. For n equal to 2, we know this. It is this square root of 1 minus 4 times x in denominator. For n equal to 3, this case 3, it's a solution of the following Hoyne equation, and this Hoyne equation satisfies to properties of so-called a priori-like differential equations, which described by Donzaguet in his paper about groups and symmetries, and it is one of these numbers 47 in this series. He described this equation. Of course, he didn't spoke about the kernel of, but the equation is exactly this a priori type equation. For generic n, we discovered this Landau Ginzburg type super potential. You remember the superpotential in my previous notations, it was a function of y with some parameters x and y, small x and small y in front of it. And this y, my series, this multiplication kernel for this, can be also related to as a period of some hypersurface of Landau-Ginzburg type. This is exact theorem which we proved. Let's consider Landau-Ginzburg polynomial, which depend on x, y, and z, and it has the following Dwork type expression. Then Poincaré residue gives you this formula, and we proved that this Poincaré residue is exactly our kernel for n formal series representation for n Bessel. So this is a very nice observation. Now, how it relates to real Calabi-Yau? That's interesting question. First of all, let's consider our Landau-Ginzburg type polynomial, our series, our solution, and consider this Batarev theorem. So if we obtain a reflexive polytope, then this family admit really, I mean, this toric hypersurface admit Calabi-Yau compactification. It is possible to check that for n equal to 3, the most interesting case, we compute both Newton polytopes for our n equal to 3 Landau-Ginzburg and dual polytope. So we have a pair of reflexive polytopes, and by Batarev theorem, they admit compactification as a Calabi-Yau. It means just that this partial case of general Batarev theorem about anticanonical hypersurface for a Gorenstein type toric Fano variety. I mean, with Gorenstein singularities. And it can be resolved to smooth Calabi-Yau Calabi-Yau variety. So this is a explicit relation with our kernel for n equal to 3, and it is checked. And then our miracle. Now I'll go to the miracle. The miracle is the following. Let's remind that all kernels satisfy to some differential equation. I showed you for n equal to the differential equation. Now it is written in terms of this theta logarithmic derivation, but it is just 4 times t minus 1. You remember it is in front of this in front of this d over dx, you have this conic for diagonal, you have this square root 1 minus 4 minus 4 times t. So this is a first order differential operator. For n equal to 3, it is second order differential operator, and in front of it you have this 8t minus 1. I showed you this Hoyne equation also from the list of Apéry-like equation of Donzagier. This is for second order for n equal to 3. And then we compute for n equal to 4, n equal to 5, etc. Here is the list up to 5. I will explain why it is interesting up to 5. We studied the types of these operators. The first, what I want to say, that they are not Calabi-Yau. But their behavior is like Calabi-Yau. We even wanted to call these operators quasi-Calabi-Yau, but I don't know. Maybe it is a little bit exaggerated. So what we speak about Calabi-Yau-like operators. So these operators, they are Fuchsian type. These kernels are solutions of these operators. They have always 0 as a singular point. And then we are interested in the monodromy property in the origins, which was important. You remember that for Calabi-Yau, in the origin, monodromy is always maximally unipotent. If we take operators n equal to 2, to 3, to 4, up to 5, everything is okay, and 0 is maximal unipotent monodromy. And we have block, Jordan block, for this maximal unipotent monodromy, and this we have this eigenvalue 0 on diagonal, and this block times 2 times 2, 3 times 3, 4 times 4. When we take n equal to 6, then it's a small catastrophe, because we have no more mum. And we have no one Jordan block. We have Jordan block times 5 times 5, and we have small block 1 times 1 with eigenvalue 1 for n equal to 6. And then the story repeats. For n equal to 7, we again have 2 blocks, 6 times 6 with 0, 2 times 2 with 1, 7 times 7 for 0, 3 times 3 with 1, up to 9, and we have 8 times 8, 0, 4 times 4, 1. But for n equal to 10, the order of our operator now 15, and third block appeared. And this periodicity, each time after 4 steps, we have additional Jordan block in the Frobenius representations. So we have no more Calabi-Yau property, but up to 5, everything is okay, and we are able to say about Picard-Fuchs operators, which annihilates this and the Picard-Fuchs operators, which annihilates our series. And we want to draw your attention for n equal to 5 specially. This is the last case with maximal unipotent monodromy. Then what we did, we compute this Picard-Fuchs operator explicitly. It is mum for t equal to 0. And then we played the same game like Candelas and co-authors played for the case of threefold Calabi-Yau period. Namely, we have Frobenius basis, and you see it is integer. The second equation Frobenius basis, which contains logarithm, is no more integer, it's normal, and phi2, of course, as well. But if we take mirror coordinate q, which is exponential of phi sub 1, phi sub 0, we again have 0. We have integrality for coefficients. And of course, we again have a mirror map, which is inversion of the series in terms of Q, and it's again integer. If we go to Yukawa potential and explicitly write it in terms of Q, of course, it's no more integer. But when we go to Lambert series, we obtain again up to this coefficient. Before it was 1 over 5, now it's 5 over 7. We have this expression with integer series n sub k, which are analog of instanton numbers. What we don't know, we don't know what the enumerative meaning of this. It means, do we have some Gromov-Witten interpretation of these instanton numbers for the case of n Bessel? There is a hint which Viktor Pjalkovsky shared with me when I gave a talk in Steklov Institute. He said that probably we should try to check if these numbers are related to some orbifold Gromov-Witten numbers. But at the moment, I have no big, big vision how to relate it. I didn't think about it, just to say the truth. I had no time to think about after, but probably it's a good direction to reflect. Now, I tell you about some combinatorics and some numerology which immediately can be obtained from our computations. Let's consider our second order Bessel. Take this kernel for xyz, not for diagonal, for any xyz, and develop it in the series over x divided by z minus y. So now our series, it is a series over x in some degree, and z minus 1 in odd degree. So if we take this representation, the coefficients are polynomials, and these polynomials in yz always integer. They have integer coefficients. Moreover, these polynomials, if you look this denominator, they are always monic and palindromic. It means that the coefficients in y and z, they are symmetric. You see, 9, 9, 16, 16. And moreover, they are not only palindromic, but they are also complete squares. So we have a kind of Pascal square triangle. We have an analog of Pascal triangle. This is triangle of these coefficients, palindromic, with beautiful properties. It's 1, 1, 1, 4, 1, 9, 1, 1, 16, 36, 16, and etc. So this palindromicity is here, monicity is here. And also we can represent these elements of this triangle in the combination of hypergeometric series with Gauss hypergeometry and with this generalized hypergeometry 3, 2, which you remember entered in the Clausen formula, but it is just it has no direct relation with Clausen, but nice representation in hypergeometric form. Then we can go further. Instead of n, we can take any, instead of 2, we can take any n and develop it in the same form, x to m, and then z minus y in denominator in degree m times big N plus 1. Then we always have these coefficients with integer. We have always these coefficients palindromic, and we have n degree analog of Pascal triangle. Then we obtain the series of numbers. For example, we can consider these coefficients from these triangles, and we check by OEs, by this catalog of integer sequences. Some of these coefficients are well known. For example, for n equal to 3, for n equal to 4. But some of them are unknown. It means they are not appeared in some combinatorial problems. I don't speak about these combinatorial problems, but it is interesting that these combinatorial problems, they relate to some so-called dig walks in honeycomb, etc. It means that all these kernels, they are not occasionally Bessel kernels. They are related. I have no time. It is another story, but probably special talk about it. How they relate to so-called Feynman integrals with sunset diagrams. It is a very amusing link, but anyway. Now, the question, if this series relate to some period formula. Yes, if we consider this generalized dwarf family with any n, it means hypersurface of sum of degrees x1, x2, xn equal to t times x1, x2, xn, then we can consider the similar Landau-Ginzburg type potential, and we have the presentation of our kernel in terms of period for this Landau-Ginzburg potential with the help of Poincaré residue like before. It's a theorem. I didn't formulate it, but it's a theorem. And I will have the end of my talk to show you more integers. Now, instead of Bessel equation, I will put so-called Pochhammer perturbation. Pochhammer perturbation, it means that I take the following differential operator. Theta, it is again x d over x, and then we take analog of Pochhammer symbol and put this theta in this Pochhammer symbol and consider eigen value problem for lambda equal to 1. Then the solution has a very nice form, similar form, and it can be represented as a series of this type. And then the kernel, then the kernel can be developed in my previous form with integer coefficient polynomial in y and z. And this is exactly the numbers, coefficients, they are n Narayana numbers. The coefficients of these integer polynomials, they are n Narayana numbers, and which are sum of n Catalan, if you want. And of course, we have a generalization of the Clausen formula, and we have new formal series with integer coefficients, but we don't know if we have some periods for this Pochhammer perturbation. So this is interesting. This is interesting open direction of studies and computations. So I think that here it is a logical end. Please, any questions for this part?
Any comments? Any questions? Maybe. Oh, okay.
I just wonder where it is Gromov-Witten invariance. And you mentioned some kind of instanton numbers, or what? What is a kind of instanton numbers?
That's what I started. It is a classically, it was a story from which I started. I told you that the classical story of mirror symmetry is here. This is the this operator, Calabi-Yau operator.
No, I think classical mirror comes from the given tally observation
And
connection.
given tally observation is that if we take all this change of variables, go to mirror coordinates, then we obtain the Yukawa coupling, Yukawa potential, and Yukawa potential now can be the difference between our Yukawa potential and this Yukawa potential, that this Yukawa potential with integer coefficients in Q. In our case, it is no more integer in Q, but if we decompose it in Lambert series like this, we obtain similar expression, but here instead of 1/5, we will have 5/7, and similarly, we will have integer coefficients. These people are Gromov-Witten. They have their number of rational curves. This is exactly number of degree k rational curves, which lie on the generic threefold degree 5 in P4.
Yes, this is observation given.
This is observation of given tally, and it was proven by Yao, Liang, Liu, and given tally. It was a real miracle that these people computed these integer numbers, and the third number, this was checked by Ehrengrut and Ströme that it is indeed the enumerative invariant, because here people didn't know what the sense of this third number, physicists, and mathematicians proved that it is indeed the this enumerative Gromov-Witten third number. And then given tally and Yao with collaborators, they proved it for any other Gromov-Witten. What we did, we constructed similar construction for different operator, not for this operator. This is Calabi-Yau, and our operator is not Calabi-Yau. Our operator, it is Picard Fuchs, but not Calabi-Yau, because it has only mum point up to 5. So it is quite different type of operator. But you see, it's this one. Much less nicer than this Calabi-Yau operator. But it has good property of integrality, and Yukawa coupling from the very beginning is not integer, but if you developed it in Lambert series, you obtain again integer sequence of instanton numbers, like it was in the usual mirror symmetry. So the question, what sense of these numbers? How they relate to Bessel, how they relate to mirror for, you know that this N Bessel, this.
Well, I also have a question. How it related to the Bergman kernel? Bergman kernel in your case, your kernel.
Yeah, it is a good question, because it means that you ask in other words, you ask the following question: how all this relate to topological recursion? It should relate somehow, because it was also very tentative to relate the kernels from topological recursion and kernels from this story. And it's exactly your question, what in fact. And what I want to say, that the only thing I know that for some spectral curves of Airy and Bessel types, similar numbers like Narayana and Catalan appear. But how they relate exactly? They should relate somehow, definitely, because if the same coefficients, if the same numbers appeared in computations for topological recursion, and computations of Norbury and Do and I forgot the Chinese guy who made a lot of computation for with Narayana numbers. I forgot his name, but it is interesting. Andrei, I don't know exactly, but it should relate somehow.
Yeah, this is a Mulas. Mulas really using topological recurrence, using integral kernel. He constructed the mirror variant of Catalan numbers.
Yes, yes, it should relate. It was very natural to explain expect that they are related, but I don't know at the moment. It's a question to open question that I always open to discuss if there is a link with this Bergman and Sige kernel.
Yes, I just one comment because Catalan numbers, Narayana numbers, not sum of Catalan numbers, but now opposite. Narayana, sum of Narayana numbers, дает Catalan numbers. You mentioned that Narayana numbers obtain the sum of Catalan numbers.
Yeah, of course.
No, it is opposite. Catalan numbers is sum of Narayana numbers. Narayana numbers is a refinement of Catalan numbers.
Yeah, but you see, Catalan appeared in the simplest kernel case for n equal to 2. It is with this function 1 over square root of minus 4 times x, and if you take it is not the Catalan numbers generating functions, but it satisfies to some differential equation. I don't remember this one. Plus, I don't remember this equation, but I even checked it myself that it is possible to. It is very close to Catalan numbers.
Okay. Any questions? Any comments? Oh, okay.
May I ask, is that the kernel is actually can be treated as you just write the potential, there's a potential we have 1 minus xi the product of 1 minus xi plus the product of 1 minus inverse xi, right? It can be treated as just 1 divided by tw and with counter integral. So can you move to the page which the potential, I forgot his name.
Sorry, what formula you mean? You speak about this?
Yes. Just kernel. So the kernel.
This is a kernel of it's a kernel with one variable, which is a parameter here. You see?
Yes.
T in this denominator, but we can write the similar formula for any kernel of with 3 variables. It's also like our observation here. This one. So we can always represent this kernel like a period.
Okay.
This is a main our theorem for this part, that there is always some d-module for the kernel function. This kernel function is homogeneous, so it can be written in this form.
Yes. So when n equals 1, it is you can treat it as just
for n equals 1. For n equals 1, it is just it's a trivial kernel. It's very simple. I showed you. For n equals 1, it is just one. This one.
Yes. So and when equals to, I thought it should have something like the like is that obey a D3 group like
So the corresponding formula is this. I mean,
okay,
it-
maybe I misunderstood
if
something.
you want, you can write this in terms of how to say, just take divided dz, this one xz plus yz. You see, and you obtain explicitly the same type formula. If I understand properly, it's very naively like this. Look, you can go to you divide by z this.
Anyway, maybe next time, just not very. It's just actually I actually try to consider some symmetries about this kernel. So for actually maybe I misunderstood something. So maybe I should have a check next time. Sorry.
Well, you can write you can write me if you want what is exactly your question, because I don't understand. For n equal to 1, it is very simple formula, and of course it's this formula. I don't know what to comment here.
We will have your presentation, and then on the next
Yes.
we
Okay.
will ask this question again. Okay.
Yeah. So I just want to say that what I'm still going to tell you, I want to tell you how to get these multiplication formulas from elementary addition laws on elliptic curve, and how it relates to the initial Buchstaber and Kontsevich type polynomials, which I mentioned from the very beginning. So this is the will sew all parts of my story in one piece. Okay?
Okay. Thank you
No, thank you.
to our speaker.